How's it going? Hey there. We've been factoring a bunch of problems in class. We've been working hard. Now we're going to see this direction or this instruction on some problems that says factor completely. And what does that mean? Well, I just want to start off with, if I asked you to factor 70, what would you do? You might have a number that's in your head already. You're like, I know. 7 times 10. Someone else is like, no. 2 times 35. And you're both correct. But if we think about factoring this completely, breaking it all the way down, sometimes it's called factoring all the way down to its prime numbers. If we factor this completely, well, 7 can't factor anymore because it's a prime number. It could be 7 times 1, but that doesn't simplify it. But the 10 can factor into a 2 times 5. And when I look at the problem on the right, the 2 can't factor. That's a prime number, so I can just bring down the 2. But the 35 can factor into 5 times 7. And now you'll see that we have factored completely. We've broken that number down all the way. And that might be easier when we deal with some harder problems, like we're about to head to like some fractions where we have to factor within them, rational expressions. Like it's going to be a little dicey. So if we know how to factor completely, it's going to help us out. So we're going to use that strategy today as we're factoring polynomials with greatest common factor. That's the topic I'm teaching you today, is greatest common factor and how to do that. But the instructions, as you get a test, whether in my class or in the future in another math course, it might just say factor completely. So when you go to factor this first problem, you might go ahead and go right to your box method. Maybe that's what you're comfortable with. And you're going to get an answer, but it might not be factor completely. Take a look if there is a greatest common factor. What's that mean? Is there something that's in common that can factor into all parts of it? And if there is, you want to find the greatest one that's going to make it easier. So do you see that there is a 2 that factors in or multiplies in to each of these? Now that I do that, it might make the box method way easier when I deal with just an x squared and just a 6, right? X squared is automatically x times x. What are some factors of 6 that get you to 7? That's the 1x and the 6x get you to 7x. So there's my 1, there's my 6. So my answer is 2 times x plus 1 times x plus 6. You're like, cool, Mr. Z, but I may have been able to figure that out earlier. I could have just gone right to the box method, Mr. Z, and done 2x squared with the 12, and 24 is not a bad number to factor. And I totally agree, but wouldn't you say that 6 is easier? So we're going to look for that greatest common factor before we get started and see if the problem can simply just get easier, right? We're just picking a strategy that's going to make things easier for us. So on the right side, I know that you might be able to factor that with the boxes. Totally cool. But if you recognize that there is a 5 as a factor of all the parts, of all of the terms, 5 times x squared is still 5x squared. 5 times a negative 25 is still negative 125. Now you might recognize this is a difference of squares over here, and you might not even need the boxes, right? So again, this is a strategy to maybe help us find some easier ways to factor the problem. X plus 5 times x minus 5. Look at, now I didn't even need the boxes. I just took out the GCF, the greatest common factor. Then I recognized it was a difference of squares problem, and I'm done. Cool. That doesn't come that easily on all problems, but if we can recognize that there is a common factor, like, oh, I know that 7 goes into that. I know that 7 goes into that 3 times, and 7 goes into 70 10 times. Now it's going to make my box method much easier. I would much rather do a box with x squared and negative 10, where I only have to factor negative 10, instead of doing box method of 7x squared and negative 70 and trying to factor negative 490. No thanks. Let's go back to that negative 10. That will be much easier. 1 times 10, where one of them is negative, or 2 times 5, where one of them is negative. How can I get 3x? I see it right here in my last one, 5x minus 2x So let's go ahead and find those final factors. X times x times 5, x times -2. Cool. Don't forget that factor out front. That 7 is part of the problem. Then the x minus 2 is a factor, and then the x plus 5 is a factor. So I have factored completely. All right, let's finish it up on this next one. I don't want to do 6 times 30 is 180. Does 6 go in? No, not quite. Ooh, 3 goes into all those. 3 goes into 6 2 times. And 3 goes into 27 9 times. And 3 goes into 30 10 times. That's going to make my box method much easier. 2x squared, 10. That means I'm factoring 20. 1 times 20, 2 times 10, 4 times 5. I'm looking for 9. There it is, 4x and 5x. X times x is x squared. Where does the 2 go? 2 doesn't go into 5 unless I want to use decimals. 2 goes into 4. So 2 goes into 4 2 times. And 2 to get down to that 10 would be a 5, or 5 to get back with that x is that. So I have my greatest common factor of 3. I have my base times my height times my base, or my length times my width, and now I have factored completely. That's it. We're complete. The end.